Good afternoon to all. This is our tutorial sessions of 5. So here the problem statement we have shared with the data sets. So here we will show that how decision tree regressions can be developed to predict, say, pore pressure. So pore pressure is one of the important geomechanical informations which is actually required for different type of reservoir studies. So let us say that we want to do some landslide problems. So landslide problems in different tectonic setting, and we want to see that say what is the fluid movements in your reservoirs. So in that case, this pore pressure information is very important and critical for designing different type of say stability related experiment. So let us say whether your formation pressure is abnormally high. So what it is important that these pore pressures information will be used to say to avoid the blowout. It is a very common phenomena, not common, very it is a hazardous phenomena in the oil industry. Once this blowout is there, that means the formation oil pressure is very high. Then the drilling mud, the fluid we injected to make that balance. So once it is high, then all oil and gas will be exploited, and there will be high chances of fire, and the whole area has to be evacuated. This type of hazards are very very severe. So in order to avoid these things, we need the petrophysicist and the geomechanical engineer needs that pore pressure information. So pore pressures can be measured in a different way, but here we will see that from the oil log data, the geophysical oil log data, how we can develop a machine learning model to predict that pore pressure. So the data which has been provided to see that there is oil log data and corresponding that synthetically computed some pore pressure data data has been provided. So here job is you have to develop a regression model to map from your inputs here. It will be the different type of geophysical oil log data like density, sonic, resistivity, porosities, and interval transient times, gamma, etc. whatever are available, and what is the pore pressure. You see, pore pressures can be measured, can be calculated by some theoretical formula. We call it the empirical formula. There is Eaton's method, there is Bauer's methods, and there are some other methods are there through which you can calculate it. So here we have provided that data set to show that how the machine learning applications can be used to predict some pore pressure. So how it has been used? So here once we develop that the machine learning model, then the trained models, it can be directly applied to the wells where pore pressure is not there, but it follows the similar geology, means it at least has some information about that the geological strata should be the similar. So in that case, to some extent we can predict it. These are the governing equations which is actually provided to calculate these ones, and here we will show that some of the examples where that pore pressures can be modeled it.
So in order to demonstrate this one, so let us say that the problems can be first understood and asked to generate these training samples, use what is the inputs here will be your log, and output will be targeted with the pore pressure. So the regression models has to be trained, has to be data, they train with the available data. So as you know that all these models we need to pass the suffer this data. Number one, you have to have the idea should be and biases for that you are training or regulated sample only towards capturing some radiation which is decided by you. So in order to avoid these things, usually these data, C2 corresponding data target, which has options for supplement. So we want to supplement one between use of sampling and supplement this data. And there will be some advantage about that your data has been separated uniformly, and the underlying data sets which is distributed around all the three types of data division: training, validation, and testing. So let us start with that. For example, say let us jump to here. In order to start this, those will be into this Coca-Cola. So they need to log into this system, and there is dash, and there is a values in there. There you can create this drive, and you can add your data as well as the seed, and so the new folder, so you can create it and see where it is there. This slide is from here also you can see there are what is the data which is what is the size where it is stored, and then you have some that development using all packages, packages are using and so you will find some of the errors when you are running this program. So once it is there, you need to sometimes update the packages because most of the things in the Python is open source that has to be updated according to the programs that has been written. So here you see this file, creating, new, insert, and then this runtime is there. So in order to actually run these programs, we have to create this runtime. Here you see this. You can run all these programs at a time, all the scripts where these are competing, or you can individually run one by one. So if you use run all, so automatically you will check one by one, but in subsequent process with some errors, you need to solve it. So in order to do that, you can individually run one by one and see where there is errors are there. So first we have to see that what type of library is required in the program. So we have some function button code. So code that what type you want library which is required for your numerical calculations and associated. There is network library which will be used for logic purposes, and we can input this file and have plot library and plot as a unity, and there are some databases which is required to be imported. Then once it is done, the data has to be passed not in because you are running these programs in a Google Laboratory. So here we need to access this data. So for the right, you can locate it where your data is, let us say on the data where you can change it by you can give the comment, and then once you run it, then what happens that you can access that program, and you may ask some time to have some connection to the Google Drive that requires to user ID. So the next step, maybe there is a problem to share a single drive config, so some error will come to the color will be shown that something takes error. There will be solutions, and Google also is there to give you a different type of apps. We help it if it is not, if it has some problems with the syntax or some versions or any other related issue. Okay, so you can see in the slide, you can find your microfile and there is associated data. And so you can also see that by running, you can see that different type of data has been used. There is a command, there is a command, there is a GPI, automatically there is a bulk density, units in our RCC, and there are 80 kilometers per second. So you can see the resistivity, porosity, there are other data that is associated with your data sets. Then you can also see that you can see the psychology, you can visualize what is the data distribution is, if there is journey by plotting these things you can see. So these are all comments related to that. How you want to with your x-axis, which is changing, increasing from surface to the surface to the perpendicular, and your y is your sigma. And by plotting these things, we can see that the different level growth. So when you are not seeing science background, and just to lead to that, this is called geometrical railroad is a method which allows the continuous measurement of the physical property directly against the depth. That means we have a equipment, say geometrical railroad, they are mounted with some solenoid, and this solenoid contains the sensor. Okay, so this is actually lower from the surface to the bottom of the wells. So we can run it from the bottom to the top and continuously it will actually record the different physical properties like indicative of density, which will actually give you the average density of the rock which is surrounding the particular solid. So there is a principle, there is a physics which is actually left to record this diode. Like that, there is a porosity there is no direct non-answer, but the porosity that we can calculate in the name of the different walls, like density of the solid walls. So there is a formula of your arching formula. By using that formula with some conditions, we can estimate typically the value of your properties, which is not directly recorded. So there is other so your rocks are becoming to reach with us reactive magnetic competence. There is a theory of the scale, so you can directly actually give you that the gamma is high. But in that case, not single star, so their gamma will be low. So by response, by seeing this response, you can identify that where this type of star is there. So the direct way is to log in that the idea about the geological successions with different rock types is there. So at the first time, you can get some idea about that. From the seeing this or logging data, you can see that from the surface depth of your well, which is used for a particular exploration purposes, how this data has been made. So this is the first time that the geologists, petrophysicists, geophysicists do in the industrial academy. What is the first time? That is the basic information about what is the geological conditions which can be inferred by seeing that idea. So let us say traditional rock elements, they only believe on the data. Compositions will follow, but that they want to see that all the data quality. So we have to different techniques for improving the quality of the data. You may have that your data has a missing error. Why the missing error will be here? You see, when you are recording the data, they will face the different complexity. Like there is subsidence, there may be a low, there may be a skipping of some of the records, there will be conditions of the world is not very favorable. So in that case, some of the data points where it may be contaminated with some noise, or if we have that, we are denominated record. So some that may be missing. So one of the simple processes in algorithm is that we have to fill out that information. Because we need that continuous information of the data pass. Then only we can interpret these things against the particular strata, or the geological strata is there, or what which can mean etc. So this is the basic data quality. So the neural network also has the continuation of that if you have that, say year 1 month, say let us say year 1, 2, 3, 4, 5 raw data is there.
and one log data is missing. Let us say you do not be able to gather it due to some
instrument problems or maybe some other problem.
So if the geological things are actually similar, actually we can develop this
This laboratory machine learning model that will take as a data which is available and make a regression analysis between the one way log with the other.
and we develop it and see if there is any machine or
Reconstruction of the log
value in between. That is one application where the data can be tuned with the help of neural networks for the machine learning. Now once this data is there, you can analyze it, that manually, that what type of things are there, whether this response is corresponding to the particular
litho-logy or no, etc.
So for that, again, you have to know also that
what type of geological information is available in that. So that will be useful for interpreting it. I have shared in the last problems that how we can classify the different type of rock types from the last tutorial. You have seen that I really want to limit
how we can concentrate the different type of rocks present in that particular geological city. That will give you a first hand to see that how we can interpret the data. That information is based on the core sample informations provided in that particular area. So what is the core sample information? You see, when we are logging the data, it may happen, it is recording the geological tool, but at the same time they sample the rock in the different depth, and that sample has been prepared it and put it in the lab for measuring the different type of physical property. Okay, but that is a costly affair because you have to collect the sample in every depth and you have to again test it all their physical property in the lab. That amounts to a costly affair, and it is not also possible that everything has to be actually measured it on the lab. You may collect the sample, but testing is also assume a huge amount of the cost for the every sample. So the neural network has had applications that suppose you have some depth sections, you have informations which is measured based on the lab, and you have a log data, then you can develop some regression model that if the known depth, if this inputs is that, what will be the output, and that once it is trained, this type of model can be extended to the deeper depth, because we are expecting that our geology is follow this type of trend in that particular area or particular wells or across the wells like that. So you can also see that by plotting these histograms, you can understand that what type of outliers can be, if there are any distributions is following the Gaussians or any other things. Using that, you can plot it, and then there is a different type of visualizations, visualization code where you can see how they have been distributed along a panel, how they are related, say how the density is related to the porosity or porosity related to the sonic travel time. So there are different type of logs you are collected and it's provided in your data sets, right? So by the cross plot, you can have some idea about that, how they have been distributed along with their histogram plot. Okay, so here you will see this is a correlation map, and it is heat map. Sometimes it is a popular heat map. From that you can have the idea about that what is the correlations among these variables, and from that also you can have some statistical inference about that how physically also it is related. Let us say you are solving a lithological problem. So the main two logs is important. One is gamma and the density. Okay, suppose you want to solve a petrophysical problem where we are looking for, say, porosity, something like that. So in that case, this neutron porosity, the sonic device porosity is a very important component. So according to the problems, actually these logs will be used in a different way, and that is the part of the physics. And from the statistics also you can see how they have been correlated. And interpret it, whether your statistics is following physics or no. So the first clustering algorithm, what is happening that we need to plot this data in X and Y and see that how they have been actually clustered it. So it may happen that, say, let us say, looking at the figure, your X and the Y, say, two different types of logs, and this plot is a scatter plot, and you want to take the inference about that what type of lithology or rock type presence in the particular geological setting. So here you will see that some of the parts, how many things are there? At least 1, 2, 3, 4. 1, 2, 3. At least three types of say rock types is present here. But if I say that, so you want to classify the three types uniquely. So whether it is possible to separate it out the three types. So looking at this figure, you see if I draw any line, so here, so if you draw a line, it's a linear line, and this is one type, this is another type, let us say. There are two types. We cannot separate it out of each of these points which is corresponding to the particular lithology or the rock type. Now we can add another line. Some extent that the yellow line corresponding to that particular types of rock is following majorly distributed. So like that we can do that, but it is not possible that all of the data you can separate it out by the linear method, because the fact that one is the projection, second thing is that the nonlinearity coming into the picture. So from the looking at the log data, we are not able to discriminate, so let us say, three types of rock present in the particular wells. So the linear method may not be able to separate it out. So there is a potential applications of the neural network. So neural networks maps these log data to the types using the sigmoid type of functions, and it is a natural nonlinear functions which will give you the better solution, at least in theory. And so these type of things has been applied in a particular wells. The data set what we have shared it, that is a different geology, but to know about that what is happening, just I am taking one examples of former students, Anmol, who he did his work, dissertation work with me, and this is a regions of the New Zealand, the area where we have used the data sets of the IODP programs, and it was asked to develop supervised and unsupervised machine learning algorithms to understand about that what type of rocks present in that. And so here we have it has been used that gamma ray, photoelectric factors, then mineral the density, hole diameters, gamma ray, all these basics logs, POA velocity, porosity are with that particular wells, which is collected under the IODP programs. And this is a hole number 1 and the 2, and see these comparisons. And this type of, say, clustering has been done initially first based on the core sample data, and he has used different type of supervised as well as the unsupervised algorithm, how this data actually consistent with the course information which is available in that particular area. Because whatever the models we are developing, it has the advantage, but it also has to explain what is at least the known geology available in the area. Then it will be more convincing to say that our models can be able to predict a data. So the raw data usually has been pre-processed it. So there may be outliers, there may be a missing value, all things should be done, because this data has to be environmentally also corrected, because there is environmental corrections which has been applied to the log data. Then scaling is a part. The scaling part, you have that there is a pre-processing, say you have to normalize these things, because neural networks, all the functions we will be using, there you will use the value from +1 to the -1 or 0 to 1. So these type of functions acts or effectively if you normalize this, the whole data, say input with this target for your supervised algorithm in a skilled, means the whole data has to be normalize it and have to range within this +1 to the -1 or 0 to 1. And they mostly will follow that normally distributed, because there are different transformation methods are there. So log normal transform, there is some transformations are there. Say we can see normalize these things, and then that based on some of the information, say let us say core sample, we need to first develop the training model. What the data sheet I have shared it, that is a limit has been provided. Say if say it is a sandstone, then what should be the density value? If it is a limestone, what should be the range of your density value? Normally, that is based on the core sample supported by some textbook information which has been written, that if your rock type is standard, this type of rock, then what should be your range of your, say, density law. Similarly for the gamma, porosity, and resistivity. So all this exercise has to be has to be done with the help of this core sample. Then only we will be confidently generate the training sample. But training sample generation is very important. Otherwise, if your training sample generation is not proper, then machine learning, whatever you do, so if you provide this garbage, it will out the garbage. If but you need to have some representative sample. Say core data may not be entire depth, but core may be collected against a particular strata. So let us say core has been collected at depth. So you just see that at a particular depth, what type of litho-logy they have inferred. Because some information should be there. Otherwise, we cannot be confident about generating these things. At least accuracy-wise, it may not be very confident about that. It may not be there, but this all the strata, it is not required. It requires some representation. Okay, so if at a particular depth, if your sandstone is there, few sample also enough, because that needs some representation. Without the representative sample, the ENN or any machine learning will fail it. That is the fact. Okay, now once it is done, then hyperparameter tuning and many other issues are there already in all machine learning algorithm. You have to divide it, see their monitoring curve at the different data interval, in training how it is, testing how it is, in validation how it is, and how we can tuning all these parameters so that your AI/ML should not overfit the data. That is a very very common phenomena in all type of AI/ML applications. So here the principal component analysis has been done, clustering has been exercised, and there is some comparisons about that, how things are there. So this is one example where you see that the two wells has been considered, and where you see this from the cross plot, you can understand that how this each of these log data is relations are there, and this right hand side is your panel which is showing actually the correlation coefficient. So this is nothing but your Pearson correlation coefficient that give you that maximum value is +1, minimum value is can be 0 or -1, and so here it has been plotted, and that will give you that how the, because this each variable with that particular variable give you the maximum correlations. That is why it is denoted by 1, and this other value, it is actually related at how statistically they are related. So from that also you can have that collinearity, multicollinearity, if it is there, from that analysis you can do that. So the PCA has been done, as I said, that it is a dimension reduction technique, as well as it is also help you that to help you that different type of analysis, like say what minimum principal component is required to explain the variance of your output, the data we have collected it. So this principal component analysis is a method where your original data can be put in other projection systems, and by doing these eigenvalues equations, by solving, we can compute this principal component, and by using the less number of principal component, we can explain that the required variance, which is actually needed to explain that the statistics, the variance of your data. So one way it can be done, and so let us say clustering technique. So we can apply this clustering technique on the raw data. With the help of the PCA also you can do the clustering. First do the PCA. On the transform data you can also apply the clustering to see that how different type of clusters are actually scattered. You see the plus sign actually denoting this is a centroid location. So what happen in any clustering algorithm? So they have a Euclidean space. Okay. Then let us say that in the space, say in a 3D space, all these data, they are each of the potential solution. Now this clustering algorithm start with that. Let us say there is one point which is a centroid. So any point in the space. Now from that it will actually, so it may be your say any point. It may be your coordinate 0 coordinate also. Now it will have that. It will measure the distance between each of these data point with some reference point. Okay, now the distance is based on either L1 or L2 norms or Euclidean geometry, what is follow. Now this distance, based on the distance, they will actually, you have to set it that if some data is beyond that particular distance, it will belong to some other class. If it is within that, it will collapse to that particular group. So like that, in an iterative way, the whole geometry or the whole space will be divided particularly, and each of these compartment, the data will be put in that component. Like that, the clustering algorithms will run, and finally it will actually give you the way that how the data has been clustered towards a particular centroid, which is actually naturally. So these type of things are based on the statistics, but this type of information also you have to compare with the geology is there. So the PCA you apply this k-means clustering, let us say, and any other clusterings, and see how all the results, whether it is a consistent or no. That has to be plus done. Okay, this is one examples of your clusterings. So it has been done. This k-means clustering has been done after the PCA. So first data has been pre-processed it, then apply the PCA, then on the PCA data, transform data, they apply the clustering and plotted that how the data point has been distributed. And from here you see some way that our original data, something like that, all these things are overlapped. But after doing that, there is some guidelines we got it, that there is some class which belongs to one type, there is another class belongs to the other type, and these show. So it is more clear compared to the original one where it has been plotted. Now dendrogram, this is another clustering algorithms. It has been used, and the interpretations of the dendrograms, it is a hierarchical clustering method, and you can see that does not require actually the initial guess. You see, in clustering also it is one type of inversion problem. Here we need to provide that the number of the clusters at a first guess. But in the dendrograms, it has been in hierarchical methods where it does not require that type of initial guess. So it is somehow we can call it a purely unsupervised type of classification algorithm. And if you look at this, that the bottom line is the total number of the data points you have considered in your data. This type of exercise can be done in the industry, oil industry, because they are handling a logs or a voluminous amount of the oil data. That is the basic. Whatever the things in the geophysics we are doing, most of the things we have to invert it. But in the log data, one variable at least we have some better control, because the depth from the surface to the from the surface to the any depth, that is directly actually controlled by us, because we are lowering the instrument and directly recording the depth value. But in other method, in geophysical method, how the properties, whatever the way it has been varying, the depth is another parameter. That has to be also again has to be estimated in the other method. So in that way, our logging methods is somewhat direct method in compared to the surface-based geophysical method. Okay, so the bottom line is actually the number of the data which has been considered. So it may be your log data, say density, let us say. So this is your density data, and this density data has been actually clustered in a compound. So they are, see how they are have been actually put in a form. Now there is a line of interpretation at this level. So at this bottom of this level, how much the data points is there? It will be almost equivalent to the number of the data which is you are having originally. Now move it to interpret this line. Some of the data has been merged because it has been, those who are similar, they have been combined it. So here you see the number of the data points or will be less. Again, if you move at this line, there will be one cluster, there will be another cluster. Here if you interpret, there is a one cluster center, another. And if you interpret this line at this level, there is a single cluster. So at what line you are interpreting, that also matters, that what type of internal say clusters which is present in that. Okay, so that way how this actually dendrogram plot can be interpreted to have our idea about. So this dendrogram has been applied to the other holes, and so this is a part of your unsupervised type of algorithms. Now we come to that say supervised algorithms, where there are as many number of the supervised algorithm is there. It is a, say support vector machine, kernel SVM, only the kernel functions which is mapping, it is a different, because we may have that different type of kernels. We may use it, say Gaussian kernel, RBF kernel, polynomial kernel, wavelet based kernel. There are different type of kernel functions are available in your SVM library. You can see which one is actually best fit your particular problem. In the machine learnings, actually that is the one problem. There is no unique combinations where you can say that this type of combination will give the best fit. So because most of our things are actually data driven, we need to tune so many parameters simultaneously. So what type of preconditions you are providing, what type of noise level is there. So a lot of things are there, because we are solving the inverse problem. At the same time, we need to actually fix so many parameters, model parameter, hyper parameters, then things are there. So that is why that there is a combination, there is no solutions like that. With these solutions, it can give you always the best fitted things. So it may vary from problem to problem, the person to person, how he is solving that problem. So random forest, network neighborhood, cat boost, these are decision tree. These are the all these are some of our tree-based algorithms. There you see the different type of hyperparameters has to be fixed it or tune it during the training. For your SVM, C is your regularization constant, and for kernel SVM, the type of the kernel functions you are using, that is also a factor. Then the XGBoost, actually it is a advanced version of your gradient boosting methods, where the learning has been faster by by using some of the algorithm we called auto-regressive methods. That means, so each of the block, each of the decision tree, they are learning. Okay. Now let us say that if you see in a parallel mode, that it will be actually sometimes it is difficult to tackle all the things at a time. So XGBoost actually, it takes that the gradient of the previous information. Previous means, suppose in the bottom level there is a decision tree, and the above there is another decision tree. And let us say in a one line, all the decision tree, they are flowing their information. Now the computations is flowing in a line of the information that the present level decision tree, they are taking the gradient information of the subsequent past. So that gives you the fact that there is a issue, there is a called this conjugate gradient and say gradient method. So what is happening? Gradient method is actually takes the information about the only the present gradient where the gradient has been computed. It does not take the gradient information of the all the previous step from where this algorithm start. So it may happen mislead sometimes that we are going for the global minima and that the directions may not be the local one. Gradient descent will give you the guidance about the on a local one. It does not take into account that in which course of line these optimizations will follow in a minimum say minimum time or minimum say steps. So like that in the gradient in the XGBoost, it takes into that gradient information not only the present state where this decision tree is there, it also takes that the past, immediate past. So there is a subscript that decision tree gradient boosting, that it takes the gradient informations, but it is in iterative way. Okay. So and it has been found that it has been providing the superior in terms of computations and in other aspect in compared to the gradient boosting. So XGBoost is the extreme gradient boosting algorithm. Random forest, we have discussed about that. In the random forest interpretation, we need to also fix this point. What maximum depth we should go, so that we should not overfit that. The model should not overfit it. The minimum number of the samples, what is the number of the leaf, what is the root, the number of the leaf and the root node, what is the splitting ratio, etc. has to be done. Like decision tree, the most of this parameter has to be fixed it. So this algorithms has been used for both the oils, and it has that comparisons that most of our things has been giving the similar, but statistically there is that XGBoost is providing that so the better resolution. Okay, so we have talked about that pore pressure problems. So here, basically, it is a regressions models where your input has to be first selected, and then your target is your pore pressure. The regressions models here, your travel time, density, gamma, caliper, neutron porosity, temperature, NMR porosity, etc. can be taken into your inputs models, and then pore pressure can be your target. Now it may be solved in your time series problems, that not only that the present state of information, let us say log, oil log and corresponding information is your input, and you have your target is your pore pressure. Now the things is that say pore pressure at a present state that may have functions about the previous depth, overburden pressure, etc. So these things can be put in autoregressive models. And we have worked on that. If you use this type of concept in a pore pressure model, it actually provides the better results in pore pressure predictions, because it takes into account not only the present state of information of the pore pressures with the log, it also takes into account the previous depth, pore pressures, and other log informations. That way, it is actually solving that what is the physics which is actually acting from the surface and the subsequent depth of pore pressure calculation. And this decision tree, there are the parameters which is there in your scikit-learn, and this where you can control and tune it, the parameters, and you can check also that what is that predictions. And then there is a standard statistic like mean square error, root mean square error, mean absolute error. What are the errors? We can print it. Okay, these are some of the examples just to show that how actually these pore pressures can be predicted. Now there is a concept called these autoregressive models with this log. We can have that with the different delay or the different time, how our pore pressures can be predicted. With different lag means, so let us say you want to predict that pore pressure in 1 step, 2 step, 3 step, or any steps. It is a multi-step pore pressure predictions model. Means it is actually taking that information of the previous state of information. Now the question here is that at what extent we can go back to predict that future. So that needs to be fixed it during pre-processing models of the model development. Okay, so coming to that problems of variograms we have discussed in the gravity, there you will see that we need to first take the data. Here we have used that, say, in a conventional variogram modelings, we have our latitude, longitude, and the depth, let us say, and it has to be initialized by the factors. Say, let us say what is the range of these ones, and what is the seal value, what is the nugget value. These are the parameters which is required to compute compute the theoretical variogram, because that are actually there in your theoretical calculations of your variogram, and that has to be first normalize it. Then the variogram modeling will be start. There from this code you can able to provide that provided x and the y, these are the lag distance. T is a variable to be actually interpolated it or to be fitted it, and this plot it, this is a plotting functions, means it is assuming that things are true, and number of the beans. So that is another important parameter, because when we are actually plotting these things, that number of beans has to be selected, because we have seen that when we are plotting a Gaussian distribution, there also we need to fix that what is the number of the beans. That actually give you that what type of distributions each histograms actually follow it. So these things has to be actually usually to start with. You can see the number of the data point. Number of the data point which is used, that can take in the initial A of number of the beans. Okay, that may decrease it because you cannot increase it. And then there is a to the variogram model fitting, you can compute that the computed seal, range, and the nugget. So that we will discuss in the theoretical graph how it is the fact, how the parameter is. So now the start with that, you have to first assume this theoretical model, that which type of model is good for your spatial interpolations. Then compute the theoretical model using the fitting that initial value like nugget, seal, and other, and then you have the data and compute this experimental variogram. Experimental variograms is that the variogram which has been computed from the data we have collected from the field. Whereas the theoretical variograms is the variograms which is computed based on the theory, like Gaussian model, RBF model, spherical model, exponential model. There are different type of models are there. So these, and they are, why it is a theoretical? Because they have the equations. So with this equation, we can compute theoretically what should be the variogram response ideally. Now you have your data which is collected from the field. Let us say it is a data of your gravity observation, gravity anomaly, or it may be a data of your, say, some pollution source, arsenic, like that. It may be have some properties of some any sample geological data which has been collected by field with the latitude and the longitude, because it is a geospatial data. Right. Now, our problem is again the least square fitting, the fitting problem. Again, the inverse problem start.
The data on which you are going to show how to calculate the value now.
Experimental data is the data which I have shared, say latitude, longitude, and the data we have shared it in the data in the tutorial. Na? So we have the latitude, we have the longitude, and we have the gravity response corresponding, we have the altitude. So it is a data only. That data, x and y is your latitude, so z is your value you want to predict it. So let us say you want to predict the gravity anomaly. So you have your latitude, you have a long.
Predict the value.
So just to see this, that this one, you see, this is your nugget, what we have defined in a variograms, and this is the range, and this is the seal. Okay, these things are actually required to define a variogram, to compute the variogram. So we have to start with that this is a spherical, exponential, and the linear. And they have that. Huh?
This is your distance and
This is the distance.
the formula is here. Yes. So this variable is the gamma. The distance formula has been provided. This is the gamma. It is the value of this variable. And we have the parameter actually required to compute this theoretically. Because you see this is a function of C, H, and W. These are all A is your range.
It is provided B is the slope from the graph, and C is the seal. So this information has to be estimated. Then only you can able to compute this theoretically, the data. So there is linear models. You see, there is a lag distance function, the semi-variance curve. This will give you that how your data, the distribution is fitted to the which type of variogram is. That exercise has to be done in every geospatial data, that which type of theoretical models is actually explaining your data distribution. Actually, we fit it directly because we have the softwares. You provide this in the server, you enter this lat value, long value, compute this gridding, they compute this interpolated method, plot it in the contour. But they essentially do all this mathematics is there in the software. There you can see that after plotting this, you can see which type of methods they have used. There is a kringing methods or co-kringing or any other inverse. There are some other methods is also there. Remember that inverse slope. Then there is some inverse. I don't remember some of the names, but these are the methods has been there in the GeoSoft, any other commercial software. Okay, so once this variogram has been done, then the ordinary kringing has been used to predict the data. Okay, so that is a part one, is that variogram fitting is over. Now next step is that once this variogram fitted is there, you want to predict with that fitted variogram to what is the value at the unknown location, where you do not have the direct observation. That is what this prediction is. So this is one example. So we have that there is a code. That first one is your original data, let us say. First one is the Bugar gravity anomaly. It is in milligel, and it has been a part of your data from our, say, Kishanganj. This data has been acquired of the Ministry of Art Science project, which is sponsored. And this data, just to using this program, we have seen that how this data is actually predicted. So the top one is the data which has been acquired, and bottom one is the data which has been predicted in the kringing. So how this has been interpolated, and this is the kringing variance. Now when we are doing this variogram fitting, so there is a variance which actually explains that we, in addition to the predictions, how the deviations, standard deviations associated with each of these data point. And this is your semi-variogram fitting which has been used. The theory what we have discussed it has been used for your Kringing type of prediction. And this is the regression fitting. You looking at that, it is a overfitted, but actually whole data has been shown for that. If you divide this data for your part of the data for your model generation and part of this, then this type of fitting will give you the less. So it is a whole data has been given, that is why it provided the 100% prediction accuracy. And if you see that fitting these variograms is not a straightforward job. They are also need to tune that so many parameters here. You see in a different context how our semi-variance looks like. That whether it is perturbed by the sampling, how much is perturbed by the sampling, how much is perturbed by the number of the data. As I discussed that if the number of the data is very less, it will be very difficult to each of these data point to fit to the original one. You see here, the different 3-4 types of data has been experimented it. So our job is to the smooth one. This is your, say, let us say the theoretical curve, and the square, these are the all points which has been calculated, which has been based on your practical variogram. So your practical variogram means these are the data which has been based on the real data, whereas the smooth one is the data, the models which is based on your theoretical computation. Now our job is to that, it is a least square fitting, that what is the minimum error with the, this is your, say, target, this is your observed. So here your observation is your data where we have collected, and this is your, say, prediction. Again, it is a least square fitting problems where you can obtain the fitting in the based on the least square sense. And this is a methods, the data driven semi-variance computing has been done. This type of flowcharts may be used to address that if there is a less number of the data is there, whether this type of things should capture the variation of the data. So in many our groundwater or aquifer related problems, we face that if our data sample is, number of the data is small, then that the original, say, Gaussian interpolations or the Gaussian models, okay, that will actually overly smooth the operation. So if you very smooth the operation, what will happen? If the variations, local variation is there, that will not be captured in your interpolated map. That is another drawback in the kringing method. Kringing means when your data is less, then the kringing based interpolation method may mislead that interpolation. You see, this problem is very prominent in our problem, those who are working in the water resources project. They have your small area where they want to collect the data by some deploying equipments or taking some sample of the water chemistry, something like that. They have a limited data. Sometimes they may lead up that in the 3 years they could able to collect, say, 200 data points or 300 data points, let us say, because it assumes the cost also. They have to test it in the labs, different chemical properties, physical properties like that. So in that case, if you directly use this kringing, what will happen that it may actually over smooth this image. So if you just do this over smoothing, what will happen? Actually the local variation, which could be an interesting phenomena, say pollution source modeling or any other things you want to map it, it will not be reflected. It will not be captured in your data, because we are actually over smooth or over smooth this process it. So what is the natural variations we want to look for, any scientist looking for, that may mislead it. So we need to select the proper variogram for your spatial modeling, then only you can able to capture the local variations. Like, say, you are estimating the aquifer, say, hydraulic properties. It is a useful not only the water resources, it is useful for the petroleum industry, how the fluid flow is like that. So in that case, if you directly do this type of smoothing, you have to be very careful about that, because if data is enough. If it is representative, there is a different story. But in cases it happens that if you go for these variations, because this type of properties is dependent on the directions. Say fluid flow and these hydraulic properties, they are dependent on the direction of the fluid flow. So what is happening that in one directions you are estimating, so you are actually neglecting the directional phenomena in that. So the variations in X and the Y, see this variation may not be captured in that. In fracture detections, let us say, fractures are any direction they can be. And their orientation is largely affect that these properties, hydraulic properties. So in what directions the fractures are there, these things has to be, if you want to explain it, then you need to properly deploy that correct interpolation method. Then only you can address or captures the anomaly. So this is one example of the hydraulic conductivity, transmissivity and other porosity parameter modeling, where semi-variograms in combinations of your machine learnings, say the automatic relevance determinations based Bayesian neural network has been used to model that how actually the semi-variance looks like. And the input variables are the lag distance.
Lag distance. So with this X and the Y, say latitude and longitude, we can compute the lag distance. The semi-variable you see.
That is the distance between the observation. So this distance is the one input, and the variable you want to predict it. Say you are interpolating hydraulic conductivity. That will be in your target. The inputs will be the lag distance and number of the beans, this spatial related information. Huh? Beans.
Number of the beans in the number of the grouping you want to use. The small unit to represents that plotting that histogram.
How is the direct interpolation? How is the direct interpolation overcomes the problem of overestimation that is being done by the Kriging interpolation?
So direct estimation means, you see, we collect the data on the field, we do not have the control. Only thing you can control it how finely you sample the space. So you may take the observations very finely, say 10-meter interval or 100-meter interval. That is up to you. If you increase this number of the samples or densely, then you could gather the as many number of the sample. But the sample has to be tested. That assumes the requires the cost also. No? Just collecting the information will not help you. We have to test that each of these data point, what are the physical property you are looking for. Let us say arsenic, you want to model it. So you have to collect the waters, we have to collect the rock samples, test it in the lab. So the number of the samples you will increase it will increase the cost of your survey. So
About Kriging interpolation vis-a-vis direct interpolation, in the sense that Kriging interpolation oversmooth or overestimates the information that is required. Yeah. So sometimes it may lead to wrong interpretation. So my question is, how is the direct interpolation overcomes the oversmoothing?
So direct interpolation is good
when you have the more number of the samples. Like if you precisely ask me that what should be the ideal cases, that at least more than 100 data sample you should have to employ the Kriging. If less than this number of the 100 or so, say you have say 30 or 40 samples, 50 samples, so in that case there is highly likely that we will oversmooth it, but Kriging naturally it will oversmooth it, but if the more number of the data is there, at least you should have some scope to make that that you can tune the some of the parameters, so that, but naturally it will over smooth it, because these Gaussians or this kringing, it actually favor the smoothing. So interpolations it favor the smoothing based on this the theoretical model. So the local variations is some of the data point which is away from this one, so that will not give you that. So ideally, if you see, so there is a theoretical curve, right? So there is a theoretical curve. Just coming to that point. Yeah. So let us say it is a theoretical curve. Okay. So if your data all are falling on the line, like the ideal case, your data which is actually calculated, all are falling in the theoretical curve. Then what will happen? It will only captures the data will have. So some points may be there. I am not saying it is outlier. Some points which are actually away. So the local variations will not be better captured by the traditional thing. Okay, but in this machine learning, what will do? It will trade off between the two, smoothness as well as some of the data points which are scattered around. So it will, what will happen? It will not very rigid towards the smoothness. It will have some flexibility to map that every data point could be fitted it to some reasonable extent. So that way, it will have some flexibility to enhance some of the local variation. That is what we want to see, emphasize it. And quantitatively, if you ask that if your data point is more, say let us say more than 100, 200, something like that, then usually both the methods, the traditional method as well as the AI/ML based method, gives the similar performance. But the problem will start the less number of the data. So with the less number of data, this kringing may not be recommended always, because it will give you model, but it will not actually captures the variations. In cases, some research paper we have published and some papers also there. Okay, so what I wanted to say that so this is one example. So you can just see that support vector regressions can be also used for map, say geospatial data, what we have, say latitude, longitude, then then altitudes, and say gravity anomaly, and to predict that interface. So the data we have provided in the synthetic one demo data is there, where your data has been normalized, and you have the map. Say let us take inputs from your first 4 columns. say latitude, longitude, altitude, and gravity anomaly, and your target will be your depth. So your target is the last column will be your predictions, and the previous 4 columns will be your say inputs. Okay, so here some of the library, common library like matplot library, pandas, has to be imported in the scikit-learn. So there is a SBR tool is available. We have to import that SBR from the scikit-learn library, and some of the metrics like mean square error, R2 square, regressions models, then how the training and testing data can be splitted it. So there is a functions is also there. All these functions are inbuilt in the scikit-learn that has to be imported it, and then there is a normalizations are there. There are as many number of options are available. One is that mean max scalar, min max scalar, standard scalars, and these are the metrics has to be imported. Then need to drive, need to access this data if you are run these programs in your Google Colab, and once it is done, then that has to be see that to access these things in the data, that which data is what. So that gives this comments gives you that this out of the data your first 4 can be your 1 inputs, and the last one will be your y. So x is the first 4, then the y is your last column, and you can by print text you can see it. Then once it is done, then you can divide it that how much the percent of the data you need to use for the training, how much it is testings. So from that comment we can split it. Okay, so back to that, we need to divide it, and you see the test size is 0.3. That gives you that 30% of your total data is for testing, and rest say 70% is for training. The random state put at 0. Then you can print it. Then this SBR models, regressions models, they uses these kernels. So kernel also you can change it. C is your regularization constant, gamma is another regularization parameters which is there in your SBR, and that the regression fit, that is give you the, this is the models which is fitting x versus y, and that will apply to your training data. And with the different kernels we can experiment it. Here is a kernel, polynomial kernel, there is RBF kernel, linear kernel, and associated that regularizations parameters is provided. So the regression speed, it is a huh?
Those are hyperparameter gamma. So in the equation we have shown that the loss functions, which is
has a 2. One is that the first part is model complexity W square, sum of order 2, and there is some C into there is some these are the hyperparameters. Say let us say we need to fix it during that training.
Just because all things are covered and they are very easy questions. So we are training and testing and splitting of the data. Then we can run this, we can print it. And after this training, you can also evaluate the different type of statistics. What is the R square, what is the root mean square, what is the mean absolute error, and
there is only one answer.
Only one answer. It is multiple choice question. Write on the name, institute name, mobile number, email ID.
So we can see the PDF you have sent.
सर जीरो नंबर आने में कोई पनिशमेंट तो नहीं है ना?
completed, you can submit it. Request to all to submit the feedback form that hard copy already. Soft copy also share. You submit it, that is also mandatory. Google form has been shared, right?
Yes, sir.
So just request to all to submit quickly. The feedback form on Google form also shared. Email. WhatsApp group it has been shared.
Just now?
No, yesterday
I shared it yesterday.
so in group it is there. So you please submit that feedback form. One Google link has been shared. So feedback is very important and compulsory.
Passport size picture.
Passport.
Passport size picture they are.
Passport size photo is required. You have to upload that individual photo in that form. And we need anyhow, the soft photo.
Yesterday's lecture.
I would ask Upadhyay sir to collect and that has to be also submitted to the Ganpur. My lecture, I will do that. It will take some time because there is validatory session, so I have to see and share it. Anyhow, WhatsApp group is there, so there is no problem. And all email ID I am having. So if I have any queries, I can increase response in time. Because there is a single point contact now after the war. You need to may require some clarification because anything has to be settled. There are MCs are there, any certificates has to be submitted. Lot of work are there. If I need something help, you just help me. So the data sheet and all these tutorials have been shared, and something we asked that some lectures and other things once to be done. Then, but the data sheet for the exercise we have shared, so you do that and come up with some solutions. I have the solutions, but provide them I can check that where it is wrong and where further improvement is required.